Okay.
I know, I saw you.
All right, you guys talk about it.
I know. Dude, I know. I went to a race yesterday. I was
Okay, ladies and gentlemen. Just to recap, if you guys look at the board, we have a couple things upcoming, so don't worry about that. Page 3 to 6, that was the intro to buffers. Okay, and I gave you a breakdown it the other day, but it is due Monday. Okay, and I gave you some select answers all the way through page 6. You'll be applying Henderson-Hasselbalch, so that will be fun. Miscellaneous points about buffers. That's a continuation of what we're doing today, so I'll tell you more about that. It's a very short video, due by A day. That's Monday. Another video, again, short. They're kind of like little tiny segments, like TikToks, if you will. Okay, it is due by B day, page 11, 12. Okay, and then owl. I have a medium-sized owl due by Thursday, 7 a.m. Okay, so that's kind of the upcoming look at a glance. Do you guys have any questions? Okay, guys, so going back to what you guys learned last night, you learned about common ion effect. So if I said, write an essay about what the common ion effect is, what would you say? Pretty simple concept. Okay, for a weak acid, what is it called when you add a common ion? You would add, what is the common ion? What do you call that? You'd add the conjugate base. If it was a weak base, you would add the conjugate acid. Now, you guys, what's the effect of it? Okay, so you guys, this is the most important example right here. So this is a normal acetic acid left to its own defenses. Its pH was 2.63, dissociated 0.7%. With the presence of a common ion, what would you say happened? Now you got this product present. Some say, oh gosh, it would shift backwards. I would like you to think that it's going to shift less forward. Do you know what I mean? How is that proven? What's the percent ionization now? Right, it went from 0.7 to 0.003. So it's not going as much in the forward direction. Do you guys see? That is the common ion effect. And as a result, since you're not generating as much H+, what happened to the pH? Not as acidic. So you guys feel like that makes sense to you? Okay. Common ion effect is also what a buffer is. A buffer is a weak acid and its conjugate base. Or a weak base and its conjugate acid. And you guys learned some math trickery. Okay. You can do an ice table to show everything we just said, or what could you use? Henderson-Hasselbalch. Okay. One last time, you guys, what really is Henderson-Hasselbalch? It's like the ice table, but the short version, okay? It does the ice table for you. So how is it defined? The goal is to get pH, so what do? pH equals, what is this? pKa. So anytime from this point forward, if I say P something, what does that mean? Take the negative log. So if I say P your birthday, could you do that? Absolutely. Negative log of your birthday. Okay, so pKa plus log what over what? What's on top? Base over acid. And folks, I will warn you, you will see Henderson-Hasselbalch written different ways because you can manipulate the math differently. But if you remember that pH equals pKa plus log of base over acid, every time, all the time, you are always right. Is that all right? Okay, like I could calculate pOH. I could do Henderson-Hasselbalch with pOH. How would it be different? Negative log of the Kb plus log of acid. I mean, I could do that, but why would I ever do that? Okay, so you guys, as long as you keep it this way, you'll always get what you want, which is the pH. Okay? All right, guys, guess what? We're going to apply all that today. Are you guys ready? So you learned a little bit about buffers on the next page. Okay, we just talked about, I would put a star by number 2. The definition of a buffer is what? A buffer is a solution of a weak acid or base and its conjugate partner. Okay, so that's our major, content so far. Okay, and we even talked about how, gosh, you got buffer. Your body's just this walking bag of buffer systems. The pH of your blood, okay, is actually managed by CO2 intake. It can be influenced by hiccups. Okay, so we will talk about a lot of those examples. Okay, maybe even in anatomy and physiology, you'll get some of them as well. Okay, but now our challenge is we're going to sort of map this all out. Okay, so you guys, buffers. By the way, did y'all get your lab submitted in the Schoology form? I'm going to grade that first thing this weekend. Okay, if your lab's not turned in via that Google form with the link and it's editable, okay, I will have to give you a 0. We all got it turned in? Good. All right, so you guys, you saw that buffers do buffer, right? They do suppress pH changes. For the rest of today, we're just going to prove that mathematically. We're going to do the math to support that. Okay, easy enough. We're going to use a base buffer system. About half of you guys use the same one, NH3 and NH4+. So first thing, start with a nice dissociation reaction. Go ahead and write it out. Write out the dissociation for the weak base NH3. It's a weak base, so where are you going to get the H from? What do you have to react with weak bases with? Yep. Okay, what are you going to make here?
H4 plus NOH minus.
Aiden, you need help finding something?
I'm submitting the lab.
Got it. I mean, if you submitted it the other day, it's already submitted. You don't have to resubmit.
Did I submit?
I don't know. I asked you guys to the other day. Okay, guys, the NH3 is going to grab one of those H's. What are you going to make? Oh, there's my conjugate acid and OH minus. Okay, nothing's changed. Letter B, calculate the pH of a 0.3 molar NH3, 0.36 molar NH4Cl buffer system. Okay, first of all, NH4Cl. Sometimes the Cl throws us off. What's the role of the Cl? Spectator. So you guys get used to the spectators. They have to be there. Can't have a cation without an anion. But just ignore the Cl. So now does it look like a buffer system? Okay. You guys have 2 ways you can solve for the pH. Can you set up an ice table? I want you to do that. Would it be appropriate to use Henderson-Hasselbalch? It would. For this one last time, I want you guys to prove that you can do both. So on the left side, I want a beautiful ice table. Okay, and on the right side, I want you to Henderson-Hasselbalch that. See, I'm telling you, it's going to be a verb before we know it. Okay, guys, I'll give you about 5 minutes to work through both of these. What kind of pH are you expecting? See, it's a base buffer system. I would sure hope it's going to be basic. Okay, so for NH3, what's our molarity? 0.30. And you guys, what's going to be unique when you got a buffer system or a common ion is instead of 0, 0 like usual, okay, now you got a number here, 0.36. Okay, which way is this equilibrium going to shift? Still going to shift forward. And what kind of K value are you using for this base dissociation that generates hydroxide? So you're going to use the same old KB, which I'm guessing you guys have memorized. Ah, I love it. Okay. Okay, you guys can solve for X, and will X be H plus or OH minus? It's going to be OH minus, so you can take the negative log of that, but will that be pH or POH? Okay, can you guys get me a pH? Back to the neighbor, help them out. It's Friday, but it feels like a Saturday, doesn't it? It's kind of my fault. I told like every student yesterday, have a good weekend, see you on Monday, bye. So I'm surprised you guys came back. Carter did it. Oh, yeah, right. So heard Nate and Jack just discuss something around 9.18.
Yes.
That sounds pretty darn good to me. You don't need to get rid of the minus X plus H.
Yeah.
Okay, now you guys, I see a lot of you starting the Henderson-Osbach, which is awesome, but you guys, there's some more to the puzzle. And I want you, as you solve, to really pay attention to each component of Henderson-Osbach. So we're looking for pH. So we're going to do negative log of the Ka, yes? Folks, you guys, I don't care if it's an acid or a base example, it is always negative log of the Ka. So what do we have to do here for this problem, since it's a base buffer? We have to convert it. Okay, so I'm going to take my Kw to the negative 14, divide it by 1.8 times 10 to the negative 5. I'm guessing some of you guys have the Ka for ammonia memorized too.
5.6 times 10 to the negative 10.
You got it. Negative log 5.6 times 10 to the negative 10. And then you guys, this ratio, make sure you put the base on top, acid on the bottom. Doesn't matter if it's a conjugate, who cares? Doesn't matter. Base on top, acid on the bottom. Who's the base here? Ammonia. So 0.3 goes on top, and then the acid, even though it's a conjugate, doesn't matter. 0.36 on the bottom. And you guys can guess, what is the most common mistake that students make using the Henderson-Osbach formula? Yeah, they get that ratio mixed up. You're quite correct. Okay, now here's the part I really want you guys to spell it out. What is the pKa? What is the negative log of 5.6 times 10 to the negative 10? Type it in. 9 point what? Isn't it 9.25? And then you guys, what about the log of that ratio? 0.30 over 0.36 comes out negative, right? Because it's a decimal. And what is it? 0.079? Is that round right? Now, you guys, I know the goal is to add these up to get 9.18, but I want you guys to appreciate these pieces for a minute. Okay, so take a pause. You guys, you remember the other day when we talked about the perfect buffer? What's the ratio of conjugate acid to base that makes the perfect buffer? If these are 1-to-1. So let's just say these were 1-to-1. Equal values, what's the log of 1? 0. So that means this would just go away. What would the pH be equal to for a perfect buffer? for this system. It'd be equal to the pKa 9.25. The reason why I say that is for every buffer system, its pH is going to be pretty darn close to its pKa. Okay? So for this buffer system, 9.25 is like the fence. Okay? That would be the pH if the base and the acid were 1-to-1. So you guys, guess what? This ratio, it's like a corrective factor. It tweaks that pH for you. So I want you guys now to look at the ratio. Base on top, acid on the bottom. What are you a little heavy on? Little heavy on the acid. So you know what? That causes this corrective factor to be negative, which is going to lower that pH a little bit compared to 9.25. So what did it come out to? 9.18. Okay. So guys, that's actually really important because you guys don't know this yet. I'm going to tell you guys about it on Monday. A little challenge called the Buffer Lab Practical. And what that is I'm going to send you in the back by yourself. And I'm going to say, I want you to make a buffer with this pH. And you will have to manipulate. It's all about that ratio. You're going to have to manipulate that ratio to get the pH you want. Okay, starting from sort of that pKa. So I want you guys to know that the basis of much of this chapter is just really working with this formula and that ratio. Okay, so you guys kind of plant that in your head for future reference. Okay, but for now, does it make sense why our pH is 9.18, just a little bit acidic compared to the pKa? Okay, good. All right, so you guys, bottom line, 2 different methods, got the same answer. Which method do you like better? Most students eventually are going to pick Henderson-Hasselbalch. There are some teachers out there that they do not allow Henderson-Hasselbalch. If you use Henderson-Hasselbalch, they give you a 0. The AP College Board did not accept Henderson-Hasselbalch as reasonable work for a little short while. Why? Because it's kind of like math trickery. You guys agree it's kind of like plug and chug? And if you do this, you lose connection that it's an ice table. And it's establishing equilibria and its common ion effect. You know, you kind of lose track of the real chemistry going on. So can I trust you guys to remember, anytime you use Henderson-Hasselbalch, you're really just doing a beautiful ice table, but shorthand. Will you guys remember that? If I can trust you, then we can take the shortcut. How does that sound? Okay, but do you see that these are the same thing? This just does the ice table for us. Okay, well, now that we got that out of the way, let's Henderson-Hasselbalch for our heart's content. Okay, so we're going to do that. But you guys, now the next part of buffers. Actually, today's point. I told you that we were going to mathematically prove that buffers buffer. Okay, so letter C. How would that pH 9.18 change if we added 20 mils of a 0.05 molar NaOH solution to 80 mils of the buffer solution? We know the buffer is going to suppress, but can we mathematically prove it? Are you guys ready? Okay, so you guys, we're going to learn something called a mice table. Not an ice table, but a mice table. Why do you guys think I added the M? Well, because guess what? Mice tables are based on moles, okay? Let's backtrack. You guys, when you look at this problem, I'm going to give you a fact. If you add strong base or strong acid to anything, the reaction goes to completion. The reaction will go until you run out of something. What does that sound like to you? I think I heard it. Limiting reactants. Doesn't that kind of sound like stoichiometry from last year? That's what's going on. This is not an equilibrium situation right now. It's a stoichiometry issue. Okay? And what's stoichiometry based on? What's at the heart of stoichiometry? Moles. So I'm going to show you guys something called the mice table. It's going to kind of, sort of, blow your mind. Okay? Now, at the heart of any stoichiometry is a reaction, yes? So you guys, guess what? That's our job. If you add sodium hydroxide, you remember, strong acid and strong base, they're the enemy. They're the ones that cause pH change, and we're trying to suppress that. Okay, so we're going to add sodium hydroxide. What can you guys say about the role of sodium? Spectator. So if it's all right, I'm just going to focus on hydroxide. Hydroxide is being added to this buffer system. If you add hydroxide to water, what happens? The pH skyrockets. Okay? If you add hydroxide to a buffer system, what part of the buffer system is going to prevent that from happening? What part of the buffer system is going to neutralize the OH minus? The acid part. What's the acid part of the buffer? NH3 or NH4 plus.
NH.
So you guys, you had to make a decision. The OH minus is going to react with the NH4 plus, the acid part of the buffer. Notice what kind of arrow I used. This is not equilibrium, folks. The OH minus is going to react with the NH4 plus until you run out of something. What are the products? What's that OH minus going to turn into so it doesn't cause a pH change?
Water.
Water. Good. And then what's left of the NH4 plus? You got it. So you guys, that is the first decision for a mice table is you got to write a good reaction. Okay, now I told you the basis of a mice table is moles. So guess what? The first entry is moles initial. But folks, I am telling you, you know, like, I want you guys to think about what a 10-point problem would look like on a test. I want to give you 10 points for a problem. How many parts must there be if it's a 10-point problem? A lot of parts, right? So you guys, what I'm going to show you is a lot of stuff has to be shown to get full credit. So if I want the moles, you got to tell me how you're going to get the moles. How do you get the moles for the OH minus solution? Well, let's see. I got a molarity and I have a volume. So what am I going to do with that molarity and volume? I'm going to multiply them. But you guys, you have to show that work. So I'm writing down all this information. In order to get the moles, I'm going to multiply the molarity times the volume. What is that? 0.0010 moles. Okay, can I do that for all of my players? So what about NH4 plus? Can you get the moles? See, I had 80 mils of buffer solution, yes? And it was, what was the molarity of that guy? 0.36. Okay, so I got the moles. Okay, you guys got to show the work. So then water, you still don't care about it. Good. But we have NH3 present, right? So that feels kind of weird. But yes, it's a buffer system. So we have weak base and conjugate acid. That's part of the 80 mils. So I converted it to liters. What was the molarity of NH3? 0.30. Okay, so you guys, that's my first entry into a mice table is moles initial, but I had to show work for how I got those moles. Now, you guys, I want you thinking stoichiometry. What's the limiting reactant? What am I going to run out of? Everything's in a 1-to-1-to-1 ratio? Yeah, so guess what? This is my LR. So you guys, the next entry in a mice table is change in moles, but guess what? It's a limiting reactant issue. So guess what's going to happen to all 0.0010 moles of NaOH? Bye-bye, we're using it up. So it's all going to go down, and the final amount of moles will be, mole final will be 0. Okay, well, here's the fun part. If all the OH minus is consumed, then what's going to happen to the NH4 plus? It's going to go down by 0.0010 as well. But there's going to be some left over. So if you subtract how much NH4 plus will still be there? 0.028. Okay, and here's the real fun part. What's going to happen on the product side? These guys go down by 0.001. What's going to happen to NH3? Yeah, it's going to go up. So change stoichiometry happens in the change. Same message. And this guy went up to 0.025 moles. So you know what you guys just did? You just did stoichiometry, but for every single moving part all at one time. I could have taught this to you last year, like in regular chem. This could be your stoichiometry unit. But what would have happened? Your head would have exploded. Okay, and that would have been sad and messy. Okay? So you guys, you've learned nothing new, but you guys are so advanced in your understanding of moles and stoichiometry that you did all the stoichiometry for every single moving part all in one table. It's pretty powerful stuff, isn't it? Okay. Now, you guys, there's one more piece. We got the moles. This guy went down by a little bit. This guy went up by a little bit. I need molarity. Because when it comes down to it, pH is based on molarity. Equilibrium is based on molarity. So you guys, the last entry into a mice table is final molarity. And you guys, interestingly enough, these mole values are diluted over what total volume? That's right, because you had 80 mils and then you added 20. So what's the new total volume? divide by 0.1000 liters for both of them. Whoops. Okay, and just remind yourself, where did that come from? The 80 mils plus the 20 mils, right? Total volume. Okay, so you guys, what's the new molarities? 0.28 molar for the NH4 plus, 0.25 molarity for the NH3, and of course the OH minus is consumed. So guys, that's the outcome of a mice table. By adding strong base, it did all the stoichiometry for all the moving parts all in one organized table. Okay? Okay, well, great. You guys, when we added that OH minus, that was a stress. So this is the outcome of the stress, but now what does the system have to do upon enduring a stress? It has to reestablish equilibrium. So you guys look at step 2. Okay, step 2 says, okay, well, now that you're done with the mice table, how will the system reestablish equilibrium? And how do we do that? You set up an ice table, but what's our cheat code? Would this be an appropriate time to use Henderson-Hasselbalch? The question is it the remaining solution a buffer system still? A buffer is defined as having weak base and conjugate acid both present. So guess what? You can do an ice table, but if you want, you can take the easy way and you can do Henderson-Hasselbalch and it will do the ice table for you. Okay? So you guys go ahead and set it up, and you guys can pull information from the last time we did Henderson-Hasselbalch, like what's not going to change. We're still using the same buffer system. Exactly. So pKa plus log base concentration over acid. Guess what? pKa is still exactly the same. What was it? 9.25, right? The negative log of the Ka. The only thing that changed is our ratio. Is just a little bit different. So according to the results of the mice table, what is your new base concentration? 0.25 molar. What is the new acid concentration?
0.28.
0.28. Okay, so go ahead and recalculate. And you guys, here's the cool thing about it. What was our buffer before? 9.18. What is it now? 9.20? Is that round right?
About.
Okay.
Basically, yeah.
So you guys, in our buffer?
Yeah.
Heck yeah. We went from 9.18 to 9.20. But you guys, here's my big question for you. You guys ready? The buffer buffered, okay? But why did it become just a little bit more basic? Remember that ratio? Omar, got an idea?
I kind of realized it's only good I don't know if there's a lab, but like a strong base or kind of like goes from a strong base to a weak base, so it still adds OH minus.
You're right. Okay, if your stress is adding OH minus, I promise you, wherever your pH was, you'll get a little more basic. Okay, but Omar, to take it a little further, you observed that, but now can you mathematically see why that is based on this ratio? Because when you guys look at your mice table, what happened to the acid part of the buffer? It went down a little bit. And what happened to the base part of your buffer? It went up a little bit. So do you guys see how we just changed that ratio ever so slightly? So that now the pH is just a touch more basic compared to the 9.18 that it was. Kind of cool, isn't it? Which is what you're saying, Omar, but now you can see it's really that ratio that really affects that. Okay? All right, good stuff. What do you guys think? Can we do this?
Yeah.
Aren't you glad you're here today? Okay, you guys, guess what? We would be delinquent if we didn't prove that buffers do work by looking at what would happen if you didn't have a buffer. So the next question, D, it basically says, oh, what if you took that same amount of base, 20 mils of 0.05 molar, and you just added it to water? Of course, what do you know is going to happen to the pH? It's going to skyrocket. Can you prove it mathematically? And you know what? I'll rephrase it a little bit, and I'm going to say it this way. What if you took 20 mils of your 0.05 molar NaOH and you added 80 mils of water? What kind of problem does that sound like? Does it sound like a dilution problem? I think that's a really easy way to solve this. Is basically, I want to know the pH of this sodium hydroxide solution, but I did add 80 mils of water to it. Okay, so M1D1 equals, do you remember? It's the simple things that seem so hard sometimes. All right, what was the original molarity and the original volume of this NaOH? 0.05 molar, 20 mils, and then what did we dilute it to? Total of, and it's always the total volume. So 80 plus 20 means the total volume now is 100. So you guys see how that works? And you remember, if you're just using the dilution formula, you can just use 20 mils as is. Units don't matter as long as you're consistent. All right, so what is your new molarity? And then you guys, once you got the new molarity of the diluted NaOH, right? Remember, NaOH is a strong electrolyte, so it's also the molarity of OH minus. So what if you take the negative log of that? Are we getting somewhere? Okay, when you get a pH, share with a neighbor. Should be an oddly simple number. You guys actually can do most of this in the head. It is 12, yes. All right, did you guys get 12? All right, M1 times V1, what's the new molarity when it's diluted to 100 mils? Okay, it comes out to 0.01 molar, which is the exponent's 2, right? So pH 12. So you guys, do buffers work? Without a buffer, the pH went from like neutral all the way up to 12. With a buffer, the pH went from 9.18 to 9.2. That's buffering. Okay, guys, guess what? I thought y'all I could teach you today. Whew, is that enough? You want more? It's your turn to practice. So on the next page, you guys have 2 examples, E and G. Good luck figuring out F. Inclusive missing F.
Where?
I don't know. Okay, guys, guess what? I'm just going to give you guys one tip. So, of course, you guys, what am I doing in this problem? Reconsider the same buffer solution, but this time, what are we adding? 50 milliliters of 0.05 molar HCl. So a buffer can only truly buffer if it buffers in both directions. Okay? All right, you guys, I want you to set up that mice table. So, you guys, who's the enemy? NaOH or HCl? I'm going to use net ionics. I'm just going to use H plus because what's Cl minus? Okay. You guys, this next thing I'm going to write, that will change. That will cause you to go on the right trajectory or the wrong trajectory. If I'm adding H plus, and that's what I want to get rid of, what part of the buffer system is going to neutralize it? The base part of the buffer. Who's the base part of the buffer? NH3. So do you guys see when you set up a mice table, you got to make sure that you're writing out the appropriate reaction, okay? So NH3 is going to neutralize the H plus. Using a single arrow, what will I make? I will neutralize that H plus by locking it up in NH4 plus. Okay, see how that works? Okay, so you guys, your mice table, moles initial change, moles final concentration, but you guys make sure you show me how you get those moles. Okay, numbers just can't like fly out of the, drop from the ceiling, okay? So make sure and show me how you get each of the mole values. Let's see, so 50 milliliters, 0.05 molar. Okay, so I got my initial moles H plus. I should work for how I got it. Okay, same thing for NH3, same thing for NH4 plus. And then pick out your limiting reactant. Do all the stoichiometry for every single moving part. Get your final molarity. Yep, they're together. When I say it, Jane, it's not really 80 milliliters each, 80 milliliters together. No, they're both in at 80.
Oh.
Wait.
Are you doing the addition? You start with.
All right.
Oh, I did. Well,
Hey guys, what do you think the LR is? LR is H plus, so that guy's gonna go down by the full amount, go down to 0. You're not gonna have any of that left. NH3 is gonna go down by 0.025, sorry. And what's gonna happen to NH4 plus? It's gonna gain. And I'll tell you guys, do you wanna know the most common error that students ever make? Is they subtract the 0.0025, they subtract the 0.0025, and then they subtract the 0.0025. But you have to add it, right? Okay, you're gonna add it on the product side. So be mindful of that. Now, once you guys get your new mole value, what is the new volume that both of these are diluted over? Yep. 50 plus 80 is 0.130. And then what's your new molarities?
0.022.
Yeah, you guys, I keep hearing numbers that I'm like, those are.
Oh, wait, that's
Yeah, that's
Oh,
kind
yeah,
of weird.
mold.
we were talking.
Okay. Yeah. Yeah. Okay, once you guys get your new molarities, that is the result of the stress. The stress was adding that strong acid. Okay, so we did all the stoichiometry for every single moving part. We have these new molarities because of the stress. How do we reestablish equilibrium? You can ice table it or Henderson-Hasselbalch that. Okay, and you guys, it is natural if you start substituting in other H's for Henderson-Hasselbalch, such as, but not limited to, Hufflepuff, Hasselhoff. Okay, Hansen. I like when you guys use Hansen. I feel like, no, that's an honor. Okay, who knows? I don't know what H's you want to put in there. So, Hollenbeck. Could be Henderson Hollenbeck. Maybe he's your friend there, and maybe he's a good bowler. Mine rounds to 9.10, but I'll take it. Okay, if you guys did this right, you should get an answer of about 9.09. Mine rounded to 9.10. But you guys, there's a lot of places for mistakes, so make sure, okay, that your numbers look good. Your molarities should be very close to mine. I rounded to sig figs. So it's pKa, which is 9.25 plus log. And you guys, honestly, what do we do to the ratio now? Compared to 9.18, our original buffer, we lost some of our base because it went down and some of our acid went up. So our ratio got a little even more heavy on the acid, yes? So compared to 9.18, does it make sense that we went down further to 9.10? 9.09, whatever you guys got. What do you guys think? Okay, so you guys, you have now learned how you can mathematically prove that buffers work. When you add H plus or OH minus, you got to mice table that to see the effect of that strong acid or strong base. Then you have to reestablish equilibrium by Henderson-Alsbach. You guys think you could do the last question? Guess what's asking? Oh, great. What if you add that same amount of acid to water? What do you predict is going to happen? No buffer? The pH is going to plummet. Can you guys prove it? M1V1 equals M2V2. Okay, so you guys, you got a few minutes. This is fourth bell. You guys, you actually have like 1 minute. You guys, did you learn something new today?
Yes.
Like really significant. So you have to review these notes. The best way to do that is to complete numbers, letters E, okay, and F. And if you guys totally get lost and you've forgotten every single thing that I've said today, there's a video that goes through E and G. Okay? You do not have to watch it if you feel comfortable, but if you want to, it's a resource. You guys, what you do have to do, don't forget about this video, miscellaneous points about buffers. When you walk in, it should be done through page 10. Okay? You guys have a fantastic weekend today. You guys learned a lot. Great job.
Yeah, I'm gonna write it out for the lab.
DIY remodeling is one of the
That's